Welcome to the last week before Thanksgiving break.
Woo!
Yeah. Hopefully you all had a chance to go do that survey. If not, please do. I want to be able to respond. On Friday, we talked about mechanism of heat. Today, we're going to go further talking about doing some heat problems, the greenhouse effect, which was going to be half of the lecture on Friday, and then try to get into thermodynamics. Now, some reminders of things before we get going. Good morning, gentlemen. Thing number one, we only have one lab between now and the end of the semester. Yeah, there's only one lab, and that's more like 3 weeks. So what are we doing tomorrow?
That's a great question.
We're having a lab final. Now, what is a lab final? For my class, the lab final is fundamentally making sure that you've been paying attention in the lab and not just letting your partner do all the work or missing doing the things that are important. So you'll have questions about, like, why do we have uncertainties? When do we have to have uncertainties? Why are units important? How do you estimate the uncertainty? You'll have to make a graph. And so on the graph, you'll have to scale the axes correctly. You'll have to label the axes correctly. You'll have to title the graph correctly. You'll have to find a best fit line and find the slope for that line. And then there's one, I know there's a lot of questions. I'll continue. The biggest part of the lab is there is a practical experience where you will be by yourself and you don't have instructions on how to do the lab. You are told, given these things, find this property. And so you have multiple ways. You'll have the equipment to do it multiple ways. And you have to say, I'm going to do it this way. Do it. I think it's pretty obvious, but you want to do more than one trial, just like in lab, so it's reproducible. You're like, fluke. And so that's going to be by yourself doing a practical thing. Okay, so we had some questions first, Max, then David. Oh, okay, nice.
Is it going to be like equations with the memorize or what?
No, you don't have to memorize the equations.
Nothing like that. Just like practical.
Yeah.
Yes or no, multiple choice type question.
Much of it is multiple choice. Some of it is short answer.
Wait, short answer?
Some short answer, yeah.
I have 2 questions. Can we have our lab manual with us?
No.
How heavily is this weighted?
It's worth 2 laps. It typically takes between 1 to 2 hours. Isabel.
Is there a study guide?
No, there is not a study guide other than looking at, whoops, I marked the wrong person, just came in. There is no study guide other than just looking at the lab guide and what you've been doing. Why do you have uncertainties? How do you make a graph? You have to answer some questions about using Capstone. You won't be actually using Capstone.
Like what buttons to push?
So finding the best fit line, we're not doing that on Capstone.
No.
Guesstimating?
Not guesstimating, you're drawing.
So you just have to be able to draw.
Is that calculated?
So like don't put it on the first.
You could, but you wouldn't get credit for it.
I mean, if we draw it and then.
You have to find the slope of your best fit line.
Yeah, so like
It has to match your line.
Okay.
y2 minus y1.
Yeah.
So.
Sorry, Dave, I'll get to you.
No, go
Okay.
ahead first.
Okay, where's this guy?
Okay, so this is pretty much one of those exams where as long as you've been paying attention in the lab and doing things like you should, you'll be fine.
That's right.
So how do we study for this then?
Well, that's what I say. In my mind, you don't study for it. As long as you've been paying attention in the lab, it should be set. Right? It's
Sometimes you like you do it and then you forget about it. So like, can you just come in and like practice or?
I mean, it's tomorrow, right?
Yes, tomorrow. But I mean, yeah, you can read your lab guide. You have that available now, not during the test.
You can put up a practice test?
I don't know about
Practice
Capstone.
one?
There is no practice.
YouTube videos?
No.
So we're on our own.
Yeah. I mean, you've been doing labs all semester. I assume you haven't. Yes, Anna.
only the first, like, but you said, like, what if your best fit line does end up correlating perfectly with those? We won't get marked off for that, right?
You won't get marked off if it does, yes. That's the correct statement is if your best fit line actually hits those. But of course, I'll choose data points where it shouldn't.
Oh, okay. Okay, like just for some of them, it like for some of the ones in lab, it has like.
And if it
direct
does,
correlations.
you still can't use those to find the slope. You have to use points that are on the line that weren't data points to find the slope. Okay, so now that we have some angst built up, I'm sorry, I'm not trying to make you anxious. I really do believe that it shouldn't be a stressful situation for you guys. Yes.
How much is the practical portion of the like the experiment portion worth?
I think it's around a third. Okay, now remember I said there's only one more lab. So this week we have the lab final, then we have Thanksgiving break, and then what do we have? A test, yes.
Wait, again, already?
I know it. And then we have one lab, and then we have the final exam. I mean, we're getting to the end of the semester.
Wait, we have a lab after the lab final?
Give us a
I'm going to do the one where we play with tuning forks. Yes.
What exactly is attendance bonus? When are you adding it, and how do you can you drop the last exam and not show up for the final?
Okay, starting at the end first. Yes, you can drop the last exam and not show up for the final. If you're happy with your grade, and I will give you updates as frequently as I can so you know where you stand. I'll actually give you a spreadsheet where you can, put in like what if scenarios like, okay, if I don't take the final exam, I'll have this grade. If I take the final exam, to raise my grade, I have to get this, and so you'll have all that rights. The attendance bonus, because you're allowed up to 3 absences at missing 9 points, I will, at the start of the final week of the semester, go through, and everyone who has perfect attendance at that point, I will mark down their 2 points for the attendance bonus. Anyone who's missed more than that, I'll put in 0 for the attendance bonus. And if you don't have a 0 or a 2 at that point, well, that means if you keep attending, you can get it.
You say absent, you mean a tardy or absent?
Well, a tardy is -1. If you're more than 5 minutes late, it's -2. If you're absent, it's -3. And so you can, for you and David, because you have another lecture each week, you two can miss a total of 12 points. Everyone else is a total of 9.
What about excused absences?
That's why I have those. Because excused absences, basically it's saying you have 3 excused absences. And it's up to you how you allocate those.
Is the grade showing down a little already excluding one test, or is that?
No, the grade will always show your top 4 once you get to 4. So it's all of them until you get to 4, and then it'll be your top 4.
So right now it's top 3.
Right now it's top 3, correct.
Oh.
But you only took 3 tests.
Huh?
You only took 3 tests, right?
Correct.
But it's just all of them.
Yes.
Yeah.
Yeah.
We'll take the 4th one.
So it's all, we take the 4th one, it'll be the top 4.
Got it.
And then if we take the final, then it will drop the
Got
7.
it. White.
Okay.
This thing's too
I think we've covered the important things that need to be reviewed before we move forward. So, 3 types of heating mechanisms: conduction, convection, radiation. Describe in words what each one of these are. Just blurt.
Conduction, convection, radiation.
Okay,
How'd you know that?
she's got all visual 80. Conduction means there's physical contact. Convection is you have an intermediary that's transporting the heat, such as you heat up air and the air blows in something, or you heat up water and then the water carries the heat somewhere else. And then radiation. Radiation is actually the same thing as light. It's electromagnetic waves. So these lights are actually heating you up through radiation. The sun heats the earth through radiation. Clearly the sun is not touching us, and there aren't that many molecules that go from the sun to hit us, but it still heats us up. So this picture here is showing examples in a house of radiation. You have a fireplace. You don't touch the fire. You don't have the smoke come into your room, but you still have the radiant heating coming from the fireplace. Convection, the windows are going to cool air. When the air gets cool, what happens to it? It does do that, but why? I want the step in between. When it cools, they move more slowly, so it becomes more dense. And then the more dense air sinks down, comes over here. The fireplace is heating up air. The hot air expands and rises, and it creates convective cycles. I put this in for the purpose of the problem we're going to do. Oh, yes, homework. That was one more thing I needed to say. In the homework problems, I think it's problem 2. It asks you for the percentage that you're going to save on your heating bill.
And then
It doesn't accept a percentage answer. So I will go through and hand grade those again. If you get credit for it, that is, if you put in like 0.11 instead of 11% or whatever your answer is, I'll leave that credit. If you put it in right and it marked you wrong, I will correct it. So there's, now that I told you, oh, I can get that right if I put, the decimal instead of putting the percentage. And, if you do that, then it saves me a little bit of work. Okay, a problem with thermal conductivity. Our first 2 homework problems were thermal conductivity. That one I just spoke about was an example. Actually, was that problem 1 or 2? I think that was problem 1, actually. Yeah. Okay, so this problem here says that if I have copper here and I have iron here, and if this separator between the two is exactly 1/2, so this is D over 2, and this is D over 2, then what is the temperature at the place where the 2 metals meet? Now, it seems a little slim on details. Obviously, my answer is going to be in terms of temperature 1 and temperature 2, but I have everything I need to get it in terms of temperature 1 and temperature 2. So if I just choose numbers, so I'm going to choose a number. I'm going to say temperature 1 is equal to, let's say, 15 degrees Celsius. And temperature 2 is equal to 35 degrees Celsius. Now we'll be able to get a numerical answer. So the first thing that you have to answer anytime you're doing a problem is, what type of problem is this? So what's our concept here? What type of problem are we working with? We're working with thermal conduction. How did Andy know it was conduction? Because we have contact between everything here. It's continuous contact. So conductivity. And so based on it being conductivity, we know the equation power is heat over change in time. Notice I don't put a delta Q because Q is a transfer. Is equal to K times cross-sectional area divided by the length and multiplied by the temperature difference. I better put delta T here or I'm going to confuse my own self. So there's the equation for the power. Now, if I look at this problem, what can you tell me about the heat that flows through here, Q iron, compared to the heat that flows through here, Q copper? This is more a logic type question. Okay, we have an answer. The copper has more heat. If you have more heat in the copper than you have in the iron, what's happening at the center between, or at the point of contact between the two? You're going to have the internal energy, right? If your heat is energy flowing, right? So you have more heat flowing to that point than leaving it. Then that means your internal energy, the amount of energy you have at that point, is going up, which means the temperature is going up, which means that that point would reach infinite temperature if we had the heat in copper is greater than the heat in the iron. Because we continually have the temperature rise as long as we kept this thing together, regardless of what temperature 2 and temperature 1 are. Yes?
I have a question about entropy. So like the entropy has to increase in the system, right?
the rule is for any process, the entropy of the universe has to remain constant or move up. You can have a specific system where the entropy goes down. For instance, we can freeze water. That's a negative entropy change for the water. But in order for that to happen, you have to have an increase in entropy of whatever that was cooling it that's greater. So the net change in entropy is positive.
Okay, but it's not even a system, it's just like a universe.
Yeah. Now, if you have an isolated system, then since it's isolated, it would be the system. But if it's not an isolated system, okay, and that was not, we're not going to talk about entropy yet today. Okay, so based on that little logic thing, now we can revise. How does the heat going through the copper relate to the heat going through the iron? If the copper was more, the temperature would rise to infinity. So that can't be the case. What?
The temperature from the copper should decrease and the temperature from the iron should increase until they reach equilibrium.
Okay, when they reach equilibrium, the temperature at the barrier between the two is going to stay constant, which means the heat flowing in has to equal the heat flowing out. So once we reach equilibrium, we're going to have the rate at which heat is flowing through the copper is equal to the power going through the iron. Otherwise, we would have changing temperature. And so that means K for the copper times the area. The area, remember, is the area of this cross section divided by the length of copper. The length of copper was d over 2. And then the change in temperature for the copper. So the copper was at temperature 2 on this side, and some unknown temperature, I'll call this temperature X in the middle. So it's going to be temperature 2 minus temperature X. So that's the power for the copper. Now let's change for the iron. K for iron. It's the same cross-sectional area. Because I did it in the split, it's also the same distance. That is, this distance here is d over 2. And then my temperatures is starting at temperature X and ending at temperature 1. So I have only one unknown in this. The only unknown is temperature X. And I say I only have one unknown. Technically, I didn't specify the values for D or A. Why am I not worried about them as unknowns? They're going to cancel out. It's on both sides. And so I can multiply both sides by D over 2 and those disappear. Divide both sides by A and those disappear. And then I have K copper T2 minus K copper TX equals K iron TX minus K iron T1. And so let's move things so we have TX is on one side. And so I have K copper T2 plus, because that was a minus, I had to add it, K iron T1 equals K iron TX. Once again, I had to add that, so plus K copper TX. Factor out the TX. And so finally, if I divide everything by K iron plus K copper, I have TX is equal to temperature 2, K copper, plus temperature 1, K iron, over K iron plus K copper. And then I look in my table for the values. So that's why I had the table here. So copper is 390, iron is 80. 390 for iron. Those units, it was, I don't remember the units. Joules per second meter degree Celsius. Temperature was, I said, 35 degrees Celsius.
Shouldn't that be 15 because you're doing iron? Or no?
Oh, that's copper, actually. I said iron, but it's copper, and it is 35. But yes, I probably need to say things correctly at the very least. And that was 15 degrees Celsius for the iron. Now, what I thought David was going to say was, don't I need to change to kelvins?
Don't think you need to.
In this problem, I don't need to because we were dealing with change in temperature, not the actual temperature. Even though I have actual temperatures here, the problem was a change in temperature problem, so either unit set would work. And so if you put this in, 390 times 35 plus 15 times 80 divided by 470, what is that, just for completion?
But if you were in Fahrenheit, you wouldn't need to change, right?
No. I would have my answer in Fahrenheit then.
Oh.
Because actually, if you look at the units, these units are canceling, and my answer is going to be whatever those units are. How much?
31.595.
So 31.6 degrees Celsius. Much closer to the copper temperature. Why was it much closer to the copper temperature than it was the iron temperature?
Isn't it because copper retains its heat more than iron does?
It's not about the specific heat, which would be about the retention, as you said. Copper is much better at conducting, and so the heat very rapidly is going through the copper. And then goes slowly through the iron.
Wait, if it goes rapidly through the copper, shouldn't it cool down faster?
No, because the copper is connected to our reservoir with, infinite amount of heat it can give. When we talk about thermal reservoir, we mean it has an infinite capacity to provide or absorb heat at that temperature.
Okay.
And so with a low or a high conductivity, it's going to stay pretty much uniform temperature. Whereas the lower one's going to have a much bigger change in temperature. Now, this has, the same idea has some real practical examples. So let's suppose that you are out on a bright, sunshiny summer day and you're walking on a wooden dock. Why do they make the dock wood? Okay. Concrete is blistering, she said. What did you say? It floats. Okay, it floats is also, but sometimes it's a fix, planted in the ground, so you don't need the floating. But the temperature is a big thing. Wood, if we look at its value here, wood is right there. That's a pretty low conductivity. Compare that to the concrete up there. Concrete is about 10 times better at conducting heat. They're sitting there under the sunlight baking. They're both going to get really hot. The wood gets really hot, the concrete gets really hot. When you step on the wood, what happens? Your foot is cold, the wood is hot, what happens? Heat goes from the hot thing, the wood, into your foot, the cold thing. And so the temperature of that top layer of wood drops down to be virtually the same as the temperature of your foot. And then you have heat that flows up through the wood, because the whole wood is hot. But because it has a low thermal conductivity, the heat then comes very slowly. And so your foot feels fine because you don't have a continued rapid flow of heat into it. You just have a sudden burst and then nothing. Whereas the concrete, you make the top layer the same temperature as your foot, and the bottom layer conducts the heat through 10 times faster, which feels a lot hotter to your foot.
But why is it that, if you kept it there, it would eventually, not be as hot?
So if you keep your foot on the concrete for long enough, it equilibrates.
Right.
Your foot doesn't feel it.
Right, because you will have drawn a lot of heat out of that concrete, and yeah, that's not necessarily a happy thing.
So we don't install ourselves in the bathtub. That's true.
Well, it's not just that though. It is that the rate of heat flow will decrease as you have to go from longer and longer distances. Because remember, the power equation was area divided by distance. And so if you depleted the heat in the first centimeter, it has to travel a further distance, and so it's going to be coming slower and slower from the farther distances. So you have a local cooler temperature where your foot has been. Okay, so that's one problem involving conduction. Now going to a radiation problem. The power for radiation, we call this, by the way, black body radiation. Why black? Because black is the most efficient. A perfectly black object will perfectly absorb radiation, and it will perfectly emit radiation. Whereas a silvered object is very bad at radiation. It has a very low percentage that it will absorb and emit. So black body, because black is the ideal color for this process. And you can affect this with like paint, although as I looked it up, most spray paints have about the same efficiency. We call it the emissivity, because they're all about the same in the infrared. They're a little bit different in the visible to give us the different colors, but in the infrared they're the same.
What about that? It's like really black. It's like Vanta black.
Yeah, Vanta black would have an emissivity that is very, very close to 1, like 0.99999. And so if you shine light on it, it's going to get hotter than, well, it's going to absorb more heat than other things would because it's absorbing so much. So this equation, the power for radiation, sigma is a constant, the Stefan-Boltzmann constant shown right there. Epsilon is called the emissivity, and that is a measurement that's between 0 and 1 that tells you how good an object is at absorbing or emitting radiation. So if we look at Diana's sweatshirt or sweater, whichever it is, it's really quite black. So the emissivity of that is very high, very close to 1. And so if she wears that outside today, the temperature's not that high, but she will be absorbing more sunlight and feel warmer than somebody who's wearing, let's take David, a predominantly white shirt. I mean, it's gray, but it's much lighter color. And so David would not receive as much warmth from the sun as Diana does, just based on her clothing. And because this black body radiation works just the same for emission as it does absorption, the net power from radiation is sigma epsilon A. Oh, I didn't talk about A is the surface area now, not cross section, but surface area. Temperature to the 4th. If you do temperature to the 4th power, what units do you need to use? You have to use kelvins. It's not a changing temperature, so you must use kelvins. So in the homework problems with this, the biggest mistake you can make is forgetting to use kelvins. The second biggest mistake you can make is temperature of the object to the 4th minus temperature of the environment to the 4th. You know what a lot of people will do? They'll put change in temperature and raise that to the 4th. That's a very different value. So make sure that you individually raise each temperature to the 4th power. So I have a problem associated with this just to help us get a little experience. You guys have seen, by the way, I just have to point this out. It made me laugh. I got this picture off the internet. What's wrong with this picture?
The back row.
Yeah. The person who put the pieces on apparently doesn't know how to play chess. This is supposed to be the back row right here. And likewise, this should be the back row there. But the person who put the pieces on apparently didn't know. So they put them wrong. Okay, but that's not the point here. You've seen these things. You have practical experience probably. Things like you're walking across the parking lot and you step off of the concrete, hot, onto the asphalt, really hot, right? Why?
Questions on the bottom of your feet.
Yes, it sticks to the bottom of your feet hot. Because it's black, it's absorbing more radiation. And it's not just the absorbing radiation, it's also going to emit more radiation, right? Because it's black. But it's primarily receiving energy from the sun. It's primarily losing energy by conducting into the ground. So the reason that asphalt is hotter is because it's conducting into the ground, but it's receiving more radiation, so it's going to be a higher temperature at the top through the balance. So we're going to do a problem that actually deals with this, although I'll tell you right now, we're not going to find the answer. Not going to find the answer because the problem is one that you need to use a computer to find the answer. Question?
If black's so hot, why are they a different color for the asphalt?
If what?
If black makes the asphalt so hot, why are they a different color for the asphalt?
Because tar is black.
Well, can't you dye it?
Fundamentally, no.
Or paint the top of the road white?
You could paint it, but then that paint would wear off probably. You had a question, Aaliyah? Why does sand get so hot? I've wondered that often because it doesn't seem like it should absorb very efficiently. But the top layer will be very hot. If you dig your foot underneath, then it's fine because it's poor conducting.
Why is the top
I think it's because it's poor conducting. It's even though it doesn't have very high emissivity. I mean, after all, sand is primarily silica quartz. It's transparent, right? So it doesn't absorb much at all, but it doesn't have anything to transfer the heat to that it absorbs because it just has air and other silica around it. So I think it's because it doesn't lose heat very easily that the top gets so hot. But for the same reason, underneath is fine. Okay, so we're going to look at this problem. So these are realistic numbers. You paint these things black. Black paint has emissivity of 0.96. And you use silver paint, not just because the Raiders are the silver and black, but because silver paint was the lowest emissivity paint I could find. And so if solar radiation is arriving at what we call the solar constant at 1,360 watts per meter squared. Now, what is a watt?
It's a measurement of power.
Power, which is
Joules over time.
energy per time. So that's 1,360 joules per second per meter squared. We actually call that an intensity, which is why I have the word intensity. So intensity is power over area. And so how much power is received by the square is going to be the intensity multiplied by the area. And so I know the power that's received by the square is the intensity by the area, but how much is absorbed? That's how much is received, but some's reflected, some's absorbed. How do I determine how much is absorbed?
Don't you use the constant for that?
I use the emissivity. So I'm going to have, right. The power of the sun absorbed is equal to the emissivity multiplied by the intensity multiplied by the area. Intensity times area was that power. So that's how much power, how much energy each second is going into the top of that piece. But it's also losing power. How is it losing power? Or losing power? It's losing heat. How is it losing heat? There's two ways the top of my paver is losing heat.
It's because the surrounding is cooler than the paper, right?
Well, actually, I've just broken up the amount coming in and the amount going out. So it has radiation going out, right? The top one is the radiation coming in. I have the radiation going out, which is going to be sigma epsilon area temperature to the fourth power. And this is going to be temperature, I'll say temperature of the top. And then we have, well, okay, I'm ignoring convection because we don't have equations for it. Yes, there is that fact. But conduction. So I'm going to have plus K for my concrete times the area divided by the thickness, which I'm putting L here for the thickness, multiplied by temperature of the top minus temperature of the bottom. So we have heat that's coming in through radiation, heat that's leaving through radiation and conduction. And once we reach equilibrium, how are those heats going to relate? If we reach equilibrium, what's happening to the temperature? It's staying constant, which means that the rate of heating has to be the amount gained is equal to the amount lost. So at equilibrium, I'm going to have epsilon intensity times area equals sigma epsilon area temperature of the top to the fourth power plus K of the concrete times area over L times temperature at the top minus temperature at the bottom. Now we have all of the numbers in this equation, except I gave you all the numbers here. I didn't read them, but you have things like it's 3 inches thick, so that's the L. 1 foot square means that its area is 1 foot by 1 foot. So we have all the numbers here. Oh, and I did tell you the earth temperature as well, didn't I? Yeah. The temperature at the bottom is 68 Fahrenheit. We have everything but the temperature at the top. But if you notice, this has temperature to the fourth times some junk plus temperature times some junk is equal to some other stuff. And that is not something that we can solve simply. So I use Wolfram Alpha. Hot tip, any class, if you have a math problem of any kind and you don't know how to solve it, you can just go to Wolfram Alpha, type in your equation, and it'll solve it for you. So the answers you get here, and of course, actually, I have the answers written on the slide because I wasn't going to solve them. In Fahrenheit, the black one would be 160 degrees Fahrenheit under these conditions, whereas the white one would be 103 degrees Fahrenheit. Pretty significant difference, right? All right, thermographs don't have much time, but these are actually looking at the radiation coming from an object. The hotter it is, the more radiation comes out. And the peak wavelength shifts. So you can see through walls by looking at radiation coming through them. Now you can't see anything like the detail you sometimes see in your TV shows, you know, like, I can't think of one, let's say Delta Force or something, you know, they do a thermal imaging and they say there's 4 people in there and this person's moving from this room to that. It's not as much detail as that would have you believe. But you can see where heat is escaping from the house, and that's an important thing. If you have a house like, let's say our house in Colorado, it gets really cold there. And so there's a lot of money lost to heat escaping from the house. So if I come out there with a camera that can see the thermal signature, I can see where heat's coming out. And then I know, well, maybe I should work in that area to try to keep it from coming out. I have not. I'm afraid to because I have a cracked window. I don't want to know how bad that cracked window affects things. The greenhouse effect. This is obviously a hot topic politically, but it's an important thing. So the first thing is, what is the stinking greenhouse effect? Do you guys know what the greenhouse effect is? Yes. Anyone else? Okay, Andy. Go for it. Tell us what the greenhouse effect is.
Okay, so gas molecules can absorb heat and take it, right? So if we have like a bunch more gas molecules than we did before, then we're going to have a bunch more heat absorbing capability in our atmosphere than we did before. So since we have direct heat applied to our planet on a regular basis with the sun, we're going to trap that heat in all of our excess gas molecules. So if we have like a crap ton more CO2, and I don't really understand how the ozone layer plays into it, but I know that part of it's like damaged and that's not good.
Well, the hole in the ozone layer is a different thing. The ozone is a greenhouse gas as well.
Okay. So-
you see it on my list.
So,
I actually,
yeah.
I should have, if I was doing this in PowerPoint, I had like the bottom 5 and then I was going to go through the rest of it. Now,
So all of those like hang on to the heat and it makes everything hotter.
yes, but there's one important aspect that you didn't bring up. These gases in the atmosphere are transparent to visible light. Now, you guys know I'm a creationist. I believe God created vision for us in the range where the sun is putting off most of its radiation, and that is where light can get through the atmosphere so we can see the sun and see the planets. If we saw in infrared, we wouldn't be able to see the sun and planets. But, yeah, really. But we can see invisible, because visible light largely comes through the atmosphere. So here we have the sun. Now notice this is incoming solar radiation, 342 watts per meter squared. That's a very different number than the solar constant we use. I forgot why this number is different, but it's not important because the percentages are what really is important. So of this solar radiation, some of it is absorbed by those gases in the atmosphere. It's a small percentage, but some is absorbed. Some is reflected, and most of it comes on through. So if you look at that, about half of the solar radiation that strikes the Earth comes through the atmosphere, hits the Earth, and is absorbed by the Earth. And small amounts reflected as well. So what is that going to do to the temperature of the Earth when it absorbs heat from the sun? It gets hotter. Now, the temperature of the Earth is much cooler than the temperature of the sun. The surface of the sun, what we call the photosphere, because it's not really a surface, is about 6,000 kelvins. Surface of the Earth is about 300 kelvins. And because the surface of the Earth is so much cooler, the radiation that the Earth emits is primarily infrared. And so we have radiation coming from the Earth, and that infrared radiation is almost completely absorbed by these clouds, or by these gases. And so that's what Andy was talking about. The gas molecules absorb the energy and hold it. They do emit some. So you see this here, the 165 plus 30. That's energy that's being radiated away from the upper atmosphere. But we have a huge amount that just comes right back down to us from the upper atmosphere. And so the process is pretty much like a one-way gate if you think about it in a general sense. Energy can come in, but it can't go out. That's the whole idea of a greenhouse. You allow sunlight to come in and warm up the ground, but then the radiation the ground gives off gets trapped in. So of course, what's going to happen? The temperature here increases, so the amount of radiation that the Earth is giving off increases. The amount of radiation absorbed by the atmosphere increases. Then the atmosphere gives off more energy until you reach a balance. Is this a good thing or a bad thing? Both is the best answer. Both. If there was no greenhouse effect, there wouldn't be life on Earth. It would be a popsicle. We need the greenhouse effect to make it habitable. But if there's too much greenhouse effect, then we have what they have on Venus. I say, there ain't no one there, because Venus has a runaway greenhouse effect. The temperature planet-wide is hot enough to melt lead because of its greenhouse effect. So it can be bad if you don't have it and bad if you have too much of it. You need to have a balance. Now, in terms of greenhouse gases, this is where things get political. I have listed here the top greenhouse gases. And water vapor, depending on where you are, accounts for 36 to 70% of the greenhouse effect. It is the dominant greenhouse gas. Al Gore didn't ever rant about water vapor. Why not?
Water is essential life.
Water is essential to life, and we don't have any effect on how much water is in the atmosphere. The Earth is, 2/3 covered with water. As the temperature of the Earth heats up, more water goes into the atmosphere because we learned that the higher temperatures are able to escape. If it's hotter water, you have more molecules at higher temperature, the more able to escape. So as the temperature of the Earth goes up, the amount of water in the atmosphere increases, which increases the greenhouse effect, right? It also, by the way, increases the Earth's albedo, and so we reflect away more light as you get more greenhouse gases as well. So water vapor is the dominant greenhouse gas, but humans are not going to be ever considered responsible for its component in the atmosphere. Carbon dioxide is the next most important greenhouse gas in terms of what it's doing. Carbon dioxide, we are very much responsible for that. It's a gas that is largely produced when we do things like burn stuff. And so that's something the Industrial Revolution has caused a great increase in the carbon dioxide in the atmosphere. Then we have methane. I highlighted methane because I have always said methane is the most powerful greenhouse gas. It's the most powerful greenhouse gas of the top ones. It's not the most powerful one. Methane, though, has another thing that's going on. I talked about carbon dioxide increases. Methane, which is a much stronger greenhouse gas, is increasing at a much more rapid rate than carbon dioxide. And so the methane production is building quicker and actually probably more of a threat than carbon dioxide in the long term. What produces methane? Yes, cows. And you and me. I went to Washington State University. I'm very proud. Go Cougs. Washington State University is the university that did the seminal research measuring how much methane cattle actually produce so that we could put a number on what they're doing to our greenhouse gases. These things down here are very small components of the atmosphere, but they're much stronger greenhouse gases. These things down here are like 10,000 or more times more effective greenhouse gases than carbon dioxide, which is the standard. So I'm not here to talk about what we should do as a society, but I'm here to make sure we know what's going on with greenhouse effect. So I do have Woo Clap set up, but we're not going there obviously in 3 minutes. What would happen if there was no greenhouse effect on Earth? We would die. We would die. There was a commercial once that people were talking about their dream for the future. We're going to have a future with no greenhouse effect. Great. We're all going to die. That's a good future you're dreaming up. Right? It would be bad. We need some, but we need it to not be out of control.
So which one of those is the answer?
If there was no greenhouse effect, temperatures would drop to an unlivable level.
Okay.
Yes, ma'am.
Population of cows, I think, has actually decreased over time because they're becoming farmers and ranchers. So how is the methane levels going up?
My understanding was the population of cattle had gone up. Maybe I'm wrong. That was my understanding. From everything I've read, the best way, if you believe that man is causing global warming, the best thing you can do is stop eating meat. Huh? That's why Chris Blake was a vegetarian. He said, it didn't have anything to do with ethics of the cattle or anything. It was because he believed that man was responsible for global warming. Yes.
A Yale article from 2016 says the cause of rapid increase in methane emissions since 2007 has puzzled scientists, but new research finds surprising culprits in the methane surge and shows that fossil fuel sources have played a much larger role over time than previously estimated.
Interesting. Okay. I don't have time to get into this. As God is my witness, we will start thermodynamics on Wednesday. Dave, I can't give you new homework because I didn't do anything new. Yeah, I won't give you new homework.
But there's two.